For this next section, 8.4, we're going to be looking at trigonometric substitutions and how they can help us with integration. These are especially useful when you have a radical as part of your integrand, and depending on how that radical is set up, whether you have a number plus an x squared inside the radical, or you might have x squared minus a number inside the radical, or you might have the number minus x squared. Depending on what scenario you have, it's going to be which of these three triangles you're going to use. So these three right triangles here are set up, one for each of those three cases that I mentioned. So in the first one, the two legs are a and x, hypotenuse, just using Pythagorean theorem, square root of a squared plus x squared. In the middle one, a is the hypotenuse, x is a leg, so the other leg is the square root of a squared minus x squared. And in the third case, x is the hypotenuse, a is a leg, and the square root of x squared minus a squared is going to be the other leg. Underneath, I have some trig functions that we can solve out for x or for that radical, and I will show you more specifically how these work as we go through the examples. The procedure for doing a trig substitution, I've got it here listed out, but what we're going to do, I actually do it in a slightly different order than what your book recommends, but I'm going to draw that triangle first, and we'll write down our substitutions from there, and then we'll plug into our integral and integrate finally. So I do number 4 first. And I want to show you exactly how this is going to work. So the first one, we're asked to integrate from 0 to 3 over 2. We have dx over the square root of 9 minus x squared. So here I've got the number minus the x squared. If I were to scroll back up, you'd see I'm going to be in this middle triangle. And I'm going to go ahead and draw that out. So just underneath here, ooh, my pen does not want to work. Let's see. Guess I forgot to turn on. Sorry about that. So here is my theta. Square root of 9 is 3. This leg is going to be x, and then down here is going to be 9 minus x squared. It's from the Pythagorean theorem. Now, from this triangle, sine of theta, remember it's opposite over hypotenuse, is going to be x over 3. So if I multiply both sides by 3, I have that x is equal to 3 sine theta. And at first you might be like, why is that useful? Well, I need dx. So if I differentiate this, dx is going to equal 3 cosine theta d theta. So that takes care of the dx. Now, the square root of 9 minus x squared. Well, cosine theta is going to be the square root of 9 minus x squared over 3. Let me scroll down a little bit. So I could rewrite the square root of 9 minus x squared as 3 cosine theta. So what does that leave me with? Well, I will deal with my upper and lower bounds in just a moment. Instead of a dx, I'm going to write 3 cosine theta d theta. And instead of instead of the square root of 9 minus x squared, I'm just going to write 3 cosine theta. You'll notice we've got a lot of things that are going to be canceling out here. And I just need to deal with my upper and lower bounds here. So if sine theta equals x over 3, then theta, which is what I'm changing this to, that's supposed to be an arrow, but I'm making not a very good job of it here. Theta is going to be the arcsine of x over 3. And this can also be written like this. So what does that mean for my upper and lower bounds? Well, for the lower one, the arcsine of 0 over 3, the arcsine of 0 is just 0. For the upper one, 3 halves divided by 3 is just 1/2. And the arcsine, or the inverse sine of 1/2, is pi over 6. So I'm integrating now from 0 to pi over 6. The 3 cosine theta in the numerator and the 3 cosine theta in the denominator are going to cancel each other out. So really I'm just integrating 1 d theta. So that's just going to be theta. And we're looking at that from 0 to pi over 6. You can already see where this is going. It's going to be pi over 6 minus 0. Which is just pi over 6.